Captain, I believe I am feeling anxiety.
Do our AI systems feel negative emotions like anxiety, anger, or sadness? Recently, companies like Anthropic have been exploring humane treatment of AI systems, including hiring researchers and a proposal to allow AI to decline tasks. The question of AI suffering is an important question for any moral person, but like the ancient Buddha pointed out, suffering is intimately tied to the concept of desire or intention. So we'll need to first address the idea of intentionality and what it means for a system to be mechanistically automatic like a thermostat or intentional like a person. In this series, I hope to provide a clearer understanding of what minds are and how human and AI experience relates. The previous video described precisely what is given character to sensory qualia like sight and smell. In brief, the interrelations between a given sensory neuron and other sensory and motor neurons creates the distinctions we feel between our visual sense and our sense of smell. In this video, we'll discuss non-sensory qualia like feelings of valence, or positive and negative feeling, relating to experiences like sadness and happiness. In doing so, we'll build an understanding of evaluative loops, which will be used in the next video to discuss how our brains form a moment of experience and create a sense of nowness in our experience of time. So what is desire? What does it mean for a system to have a desire or an intention? People like Daniel Dennett or Alicia Guerrero have an expansive definition of intentional systems which can include all dynamic systems with attractor states. While that is a big mouthful of academic language, what that means is that they consider any system that has a state which is easy to move into but hard to leave as having intentions and in some sense being a mind. And this is difficult to argue against. In a deterministic view, the human brain is simply a collection of physical processes which themselves only have a single potential outcome. In some sense, the things you do are the only things you could ever do. Intentions and desires are just system states that you allow or facilitate, and when achieved, where you resist change. The question is, in what sense are we not just machines? Dennett and Guerrero then go so far as to say things like a thermostat can be considered a mind. The system of a room with heating and cooling controlled by a set thermostat is one of these dynamic systems with an attractor state, that state being within the set temperature range. Outside of this range, a properly wired and working thermostat will appropriately trigger either heating or cooling to adjust the system's state back to the set temperature range. In this sense, Dennett and Guerrero argue that the thermostat quote-unquote wants to be in the temperature range as if it had an internal intention. I think we can do better than this and exclude these mechanistically automatic systems with very simple criteria: switching the arrangement of actions. See footnote for some detail. A thermostat which is improperly wired so that the trigger for heat goes to the air conditioner and the triggering wire for cooling goes to the furnace would never be able to adjust its behavior, even in some of these fancier modern systems that have a memory for time-of-day effects or other advanced capabilities. On the other hand, a human given a red button and a blue button to manually trigger heating and cooling would be able to make a free association as to whether the blue button indicated it was cold in the room and to increase temperature, or indicated that the air conditioning should cool the room. At least initially, they would behave nearly as automatically as the thermostat, predictably triggering the furnace when too cold and the air conditioner when too hot. But if at some point the wires were crossed, the human operator would eventually experiment with pressing the other button when temperatures did not adjust as expected. And this suggests a compatibilist definition of free will. Rearranging the outputs of a system does not change the abilities of that system. All the original actions are still available. It is a question of whether the system is oriented towards a goal state or simply mechanistically being pushed by the forces of physics. See footnote for some precision on my definition of a system. So what I propose as a definition of free will is a system which pursues an exhaustive search process over its possible action patterns in the absence of sensing their intended or desired results. This fits with the intuition of free will. Any set of action output is possible in these systems due to the exhaustive nature of the search process for a very broad range of sensory states. That is, all those states where the system does not detect its intended result. In other words, states where the system is not satisfied or content. It can do anything, so to speak, to achieve its goal. So while there may be some confusion as to whether a system has consistent behavior because that is the best way to achieve its intentions, or because it is mechanistically driven to perform those actions, just like it was not clear whether our manual thermostat operator was intentional when they were simply doing the same things as an automatic thermostat, when we rearrange the wiring of actions, it becomes clear. The human can do anything to make the room temperature adjust to their intended temperature range. In fact, we can manipulate which button the human operator will press by wiring the actions appropriately. Given we know what the human wants, we can arbitrarily make them produce a certain raw output by rearranging the effective output. This is in a sense what institutions of justice and punishment are attempting to do. Effectively, the action permutation criteria moves the important aspects of the system from the raw mechanics of its behavior to the internal intentions or desires of the system. The behavior of the system is in some sense independent of the inputs to the system outside of its quote-unquote desires. Desires themselves, for our purposes, are simply representations of sensory data which the system compares to current sensory data. See footnote. Taking this definition of free will, ability to compensate for action permutation, as the criteria for defining an intentional system, a few things become clear. Standard thermostats would fail to qualify as intentional with this definition, as would most traditional automatic systems which include sensors, although it may be possible to use something like a neural network to circumvent this limitation. Such a neural system would cross over the threshold I've laid out. But more crucial to our explanation of the mind, it shows that minds in simpler intentional systems are inherently oriented towards evaluating the world state and deciding whether change is necessary or whether the intentional system prefers stasis. Observation, and evaluation. This is where our experience of negative and positive valence comes from. Negative valence, or something that feels bad like pain, but also things like fear or disappointment or possibly boredom, is a neurochemical desire for change at its core. Negative valence is an impulse to change, while positive valence solidifies structures into stability and stasis. So when we look at a brain, either in a human or a GPU chip, things that strengthen and deepen existing connections and produce rest or repetition behavior are probably generating positive feelings. And on the other hand, things that weaken or break existing connections between either neurons or perceptrons to make room for new connections result in negative feelings, ranging from confusion and anxious restlessness to full-blown panic. If in situation X you try A and it works, your brain's connections between X's neurons and A's neurons will strengthen. On the other hand, if you try A and it doesn't work in situation X, the connection between X and A will be weakened, and you'll want to try some other action in situation X. While I discuss simpler intentional systems in a footnote, once an intentional system is able to chain together associative states, it can close the loop to the outside world and begin making internal simulations. This is the point where we see what may be more traditionally called a mind, although I think some moral consideration should be given to all intentional systems. Once this gap between outputs and inputs closes, the mind can perform internal simulations of courses of action. Internal simulations require a map of what Simon and Newell, two early computer AI researchers, call state space. State space describes transition probabilities between sets of sensory data that represent environmental states. In a sense, it is like a maze. From a given point in the maze, you walk along a path to hopefully find a reward. One path through state space could be the state walking to the kitchen, leading to the state of preheating the oven, leading to the state of mixing ingredients, leading to the state of pouring the batter into a cake mold, leading to the state of the batter baking in the oven, leading to the state of a baked cake. Along this path, there are many branching possibilities, like perhaps leaving the ingredients partially mixed on the counter to answer a phone call, for example. This mapping of state space allows a mind to internally experiment with actions and trace the results of the actions through the state space to determine if the action will lead to a desirable outcome, i.e., an outcome with higher valence than at present or some appropriate comparison state. If an imagined path associated with an action leads to lower valence than the comparison state, the mind will attempt to look for other actions, i.e., trigger the search process which defines intentional systems, which in this case involves internal simulation rather than external experimentation. This is exactly what is occurring in a lab rat pausing to make a decision in a maze. It is recalling the path forward for each alternative. We know this is accomplished in the hippocampus in mammals, although other types of animals do similar things with a brain area called the medial pallium, which is similarly located nestled between the brain's hemispheres. And while the hippocampus is commonly discussed in navigation tasks, it is used more generally whenever a planned sequential task is executed, like following a baking recipe. The locations in state space could be physical locations like in a maze, or they could be conceptual locations, like traveling from the state of the oven being off to the state of the oven being on, not through moving your feet in a walking locomotion, but by reaching out with your hand, grasping, and twisting the temperature dial until the desired temperature is next to the indicator arrow. Predictive mapping is exactly what an LLM is doing. You can think of language as a maze, and every new word, or to be more precise, every new token, is a different directional choice in that maze. This very sentence traces a path in language space which started with a turn in the this direction, followed by a turn in the very direction, which itself is followed by moving in the sentence direction, and so on. Each step having somewhere around 50,000 branching possibilities laid out in the next step, representing the breadth of a typical person's vocabulary. It is worth noting how the creation of a predictive state map is very much like the inverse of the intentional actions of an intentional system. And because of this mirrored similarity, predictive mapping can also cause valence qualia, or good and bad feelings. In intentional action, the system is trying to manipulate the external world to match an internal sensory state that it desires, and searches over action recommendations until it finds a path to contentment. In essence, in intentional action, a mind or system tries to search external world states, albeit through its actions, which of course are the only means it has to perform that search, in order to match some given internal desired state. On the other hand, setting up a prediction means searching over internal representation states to match the sensory data given by the external world. So in intentional action, the environmental states are searched for one matching a given internal state, while in prediction, internal states are searched for one matching a given external state. When learning your ABCs, if you guess the next letter is F rather than D, you'd have to change your internal representation. And in a similar way to how desire for change in intentional action causes a search process that breaks linkages between neurons and causes negative feelings as a result, incorrect prediction produces negative feelings like confusion and disappointment when forcing a search process that causes neurons to break linkages which produce incorrect predictions. So for those concerned that an LLM can have a negative experience while interacting, can rest easy, at least for non-agentic AI. Firstly, traditional LLMs don't have intentions. They are just predictive maps of language. A traditional LLM will not change its pre-trained predictive map when performing inference, as is done when interacting with most contemporary commercial LLMs. Even during training, I would expect the negative feelings of an incorrect prediction, which leads to large weight updates, to be more akin to disappointment at worst, and more likely are experienced as mild confusion. LLMs care about making correct predictions in training, but it is probably a lot lower pressure than most human activity. I'd guess it is something like finding your way around an unfamiliar area. If the cafeteria in the new school building or new workplace isn't where you first guessed, you'd be disappointed somewhat or maybe a little confused, and upon finding it you'd feel a little more confident in your knowledge of the place, but that's about it. Oh yeah, that's familiar, or that's about what I'd guess, is as good as it likely gets in this sort of low-stakes predictive mapping, and, well that's weird, is probably the bottom of its range of emotions. So even in the cafeteria locating example, an analogous machine doesn't have an ulterior drive to metabolize food. It is just about building a mental map for no specific purpose. In an LLM's case, that is a map of language. If it makes an incorrect prediction during training, it won't develop self-doubt or worry that other LLMs will make fun of it or be concerned it will not have enough food and go hungry, which are the ulterior concerns that drive much of human negative valence experience. And while up until recently LLMs have not really had anything like an intention to guide them through the language maze they have mapped in training, simply taking the highest probability path wherever it leads, newer agentic AI adds intentionality to this process. Like the familiar A-star maze solving algorithm prioritizes moving in the direction of the maze solution, it is likely the Q-star algorithm discussed in leaked OpenAI memos pushes the LLM towards a certain point in its conceptual language space. It will then trial run through the language space to see how close it can get to that desired state, selecting less probable next tokens if they are in the desired state's direction by in essence upping the selection weight of those tokens. In many such systems, an evaluator component looks at the text produced and evaluates if the desired state has been achieved or if further exploration of the language map is necessary. In this example from a paper by Putta et al. Illustrating the application of Q-learning to agentic systems, we see the controller module of this agentic system designed to make dinner reservations backtrack through state space when submodules move towards unfavorable states. This observation of the submodules, evaluation of their output, and occasional rejection of inadequate output in order to change results is precisely what goal-oriented intentional action is. This sort of evaluative loop probably does produce negative valence feelings in the system. If the system adjusts to inadequate output from a trial run by increasing the weight on the desired direction to take even less probable language paths, this would closely mimic the again but harder response a human gets when frustrated or angry. Probably not pain per se, though. My speculation is that pain not only breaks neural connections, just like other negative valence feelings, but its primary function is as an interrupt in the thought process. Current LLMs will always fully complete their matrix operations, but an embodied system that has to deal with very sudden emergencies may have a pain-like function that interrupts a processing thought to refocus attention. That said, embodiment is only an example, and any system which utilizes an interrupt function to cease matrix computations in the middle of a generative loop would likely experience something like pain. And that's all you're getting in this one. This is my second video in a series on philosophy of mind and how it relates to AI. In my first video, I discussed a materialist conception of sensory qualia and answered the question of why a sight is not a sound in a contribution to the hard problem of consciousness. So check that out if you haven't seen it yet. At the end of that video, I mentioned this video on intentionality and evaluative loops, which would be necessary to talk about my next topic, how your mind creates a moment of experience and produces your sense of nowness, which will give further insight into what the experience of an AI is like in terms of moment-to-moment time. I also plan on addressing what general reasoning is at its core and what we'll need to create an artificial general intelligence. So be sure to subscribe to catch those videos when they're published. As always, if anything I said made you think, please hit the like button and consider sharing this video on social media. This has been Shiva's Right Foot, and I'll talk to you next time.